Hey everyone, here's a quick little screencast on how to work through the calculations to determine the specific heat of a metal. First, we're going to talk about what specific heat actually is. So, specific heat is something that we use to measure heat transfer between substances. We measure heat in a variety of different ways. We use calories when we're talking about food here in the United States, which is the amount of heat that it takes to raise the temperature of 1 gram of water by 1 degree Celsius. In the scientific community, we don't use calories usually. We usually use joules, Joule. Okay, then a joule is roughly going to be a quarter of a calorie. So the specific heat is a physical property which can be used to differentiate between lots of different substances. Okay, specific heat is given the symbol lowercase c. Capital C is reserved for carbon, and it's the amount of energy required to raise the heat of 1 gram of a substance by 1 degree Celsius. And we use this equation here in order to figure that out. Q, which is the heat quantity, is equal to the mass of the substance times its specific heat and the temperature change that occurred, delta T. Our delta T is always determined by taking the final temperature minus the initial temperature. You can also rearrange this equation to be C equals Q over M times delta T to determine what the specific heat of your substance actually is. So what we see is that we are going to use a calorimeter. A calorimeter is our device that's used to measure heat. We can use a really crude one, a nice rudimentary one, a styrofoam cup. I usually nestle mine in a beaker so that there is some air that insulates between the table or the desk and the actual substance. It has water inside the calorimeter, and we are going to take some metal that has been boiling in a hot water bath and hot water bath that has been boiling for 10 minutes, and that would be at 100 degrees Celsius. And then you transfer it in and watch the temperature of the calorimeter water increase. Okay, this is a very fancy bomb calorimeter where you don't lose any insulation and any heat to insulation, and literally something is heated and then dropped immediately into the water. So this is a very fancy one, but these work just fine. Okay, so specific heat has units of joules per gram degree Celsius. Water has an absurdly high specific heat relative to other things, and metals have very low specific heats, which is why we use metal to heat things up and water to cool things down, because it can absorb a lot of energy. Water has a specific heat of 4.184 joules per gram degree Celsius. It's almost twice that of ice and twice that of steam. So that's what makes water able to cool things down quite easily. So when using a calorimeter, we are going to use the Q equals mc delta T equations. And we're actually going to use two of them because the heat that's gained by the water in the calorimeter is going to get hot because the heat that's lost by the metal gets transferred to it. So the Q of one thing is equal to the Q of the other, but with a negative sign. The water in the calorimeter gets hot because the metal loses its heat, and we know all about the law of conservation of mass and matter. So if we take our mc delta T and plug it into both of these, we essentially get this equation down here. The C, M, and delta T of the water in the calorimeter is going to be used to determine what the C of the metal is, as long as we can mass out our metal and we can say what the temperature change of our metal is, which we can. So I recorded a video of me doing this lab, which is viewable right here. We'll view it together. But essentially what we end up seeing is this, okay? The metal that is used is tin. The metal has a mass of 51.42 grams. The tin metal sample is heated in a hot water bath for 10 minutes at 100 degrees Celsius. This is the initial temperature of the metal. After 10 minutes, the metal is assumed to have that same temperature, and it's poured into a simple calorimeter containing 100 grams of water, which has an initial temperature of 20.6 degrees Celsius. So this is the TI of the water in our calorimeter. The hot metal transfers its energy over to the water, and both come to a point of 22.5 degrees Celsius. So the metal cools down to this temperature and the water heats up. This is the equilibrium point. This is where both equal and the heat is known to be transferred. Knowing the specific heat of water is 4.184 degrees Celsius, we can determine the specific heat of the metal. So let's run through that calculation. Okay, so we have two sets of problems to do. First, okay, we are going to plug in the Q of our water in our calorimeter. This is, this is what we are solving. Okay, so we are looking for this. Okay, the mass of the water in the calorimeter is 100 grams. The specific heat of water is 4.184 joules per gram degrees Celsius. The temperature change of the water, it went initially from 22.5 degrees Celsius over to 20.6 degrees Celsius up to 22.5 degrees Celsius. So what I'm going to do is I'm going to subtract those two. So I get a temperature change of positive 1.9 degrees Celsius. So first, I'm going to figure out what the Q of the water in the calorimeter is. So the Q is equal to mc delta T. Okay, the mass is 100 grams. C is 4.184 joules per gram degrees Celsius, and the delta T is 1.9 degrees Celsius. I'm going to plug that all into my calculator, and I get a Q of 794.96 joules. Okay, we get our grams and grams to cancel out, Celsius and Celsius to cancel out, leaving just our joules right where they are. Okay, this is how much energy our water in our calorimeter gained. So this is exactly how much the metal lost, but it's negative 794.96. The negative sign shows that it was lost. The mass of the metal was 51.42 grams. The specific heat is what we are looking for. The delta T, the metal started at 100 degrees Celsius and went down to 20.6. So 20.6 is our final. Let's get rid of this negative sign right here. Minus 100 degrees Celsius is going to give us a delta T of negative 77.5 degrees Celsius. Notice that this final temperature is in two places. That's what connects the Q of the water and the Q of the metal. Okay, so I'm going to use this in my second part. And in this second part, we're going to figure out what the specific heat of the metal is. So we're going to rearrange into C equals Q over M delta T. Okay, my Q is negative 794.96 joules. I'm going to have a mass of 51.42 grams. And then I'm going to have a delta T of negative 77.5 degrees Celsius. That is going to go in my calculator very carefully, okay? In my calculator, I have to be aware that I have two things in the denominator. So I would type negative 794.96 then divide by 51.42, divide by 77.5. And my equals will be 0.199 joules per gram degrees Celsius. So is this our specific heat of tin? Well, according to the periodic table, and here's all of our answers right here. According to the periodic table, the specific heat of tin is 0.228. So if I'm determining my percent error, I have to take 0.228 minus the 1.99 over the 0.288, and I end up with a 12.47% error. So what were some of these sources of error? And most likely the error is going to be because of our calorimeter. Okay, I had this other beaker over here that is going to contain our hot water bath with our metal inside of it. And then I had to pour it in here. Well, that 2 seconds that it took for me to do that is exposed to the air, and some of the heat is lost. Okay, in a fancy bomb calorimeter, what ends up happening is that this immediately just drops in. There's a little button that is pushed, boop, and it never gets exposed to the outside air. So most likely it has to do with losing it to the surrounding air. And that is how you determine your specific heat from one of your experiments.